So, modern atomic theory. Atomic theory is the idea that all matter is composed of atoms. And it came out of some observations and laws, specifically law of conservation of mass. We've talked about that one. Law of definite proportions and law of multiple proportions. And we'll talk about both of those now. So, a review, law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed. And this came from Lavoisier's work, 1789. So, when a chemical reaction occurs, if you take the mass of the matter that you're starting with, everything that you start with, you find the mass of it, you do the chemical reaction, and you find the mass of all the things you end up with, it's the same amount of mass. This is consistent with atomic theory because atomic theory says that what happens in a chemical reaction is that you're taking the individual atoms apart and putting them back together in a different way, but all of those atoms are still there. So building with Lego bricks, say you've got 100 Lego blocks and you make some crazy monster out of them. You could put that on a balance and find out how much it weighs. And then you take those bricks apart and you make two smaller monsters. Put those on the balance. Are they going to weigh more, less, or the same as what you started out with? The same, right? It's the same bricks, you just put them together differently. This is the basic idea of atomic theory. So here's an example. A chemical reaction here between sodium and chlorine. The element sodium is a metal. It's rather soft. You can cut it with a table knife. Here's chlorine gas. It's yellowish gas. It's toxic. If we were able to zoom in and look at the atoms, we would see that sodium atoms, they're not purple, but I use colors somehow. They're all lined up together in a nice crystalline form, very close together. This is a solid. Chlorine is a gas. It's not formed of individual atoms, but of pairs of atoms in molecules, and they're floating around, moving through space, and there's a lot of empty space between them. So, if we took 7.7 grams of sodium and 11.9 grams of chlorine, that's a total mass of 19.6 grams. We react these chemically, and we get table salt. Now, sodium metal reacts violently with water, so you wouldn't want to ingest that. Chlorine gas, if you inhale it, does severe damage and can kill you, so also not good. But you put those together and you get table salt, which is at some level necessary for life, right? Of course, like almost anything, if you have too much of it, it'll kill you. Well, what's the mass of sodium chloride that gets made? 19.6 grams. Because all of the purple particles here and all of the green particles, atoms here, are still present. They're just put together differently. That's the law of conservation of mass. Any questions? So let's see if we can answer this question. When a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. I think we'd all agree with that. What happens to the matter that composed the log? A, the matter that composed the log reacts to form gases that are released into the air. B, the matter that composed the log is converted into energy. Or C, the matter that composed the log is still present in the ashes but has a much lower mass. They all kind of sound scientific, right? So make your own choice in your head. And the correct answer is A. The matter that was in the log is still present in the universe, but we don't see it in the campfire anymore because carbon went into carbon dioxide and hydrogen went into water vapor, and those are gases and they float away.
So does it have to be converted into a solid liquid or gas?
Pretty much it has to be solid, liquid, or gas, yeah. There's a fourth state of matter called the plasma, but that's a very specialized thing we don't talk about in general chem.
So temperature, like burning the heat, that doesn't really affect the mass. That's just a process.
Yeah, so the temperature, the heat generated by burning the wood does not affect the mass. And then, so we might ask, well, then where does it come from, right? It has to come from somewhere. It comes from stored chemical potential energy within the wood. So what happens when the wood burns is that the cellulose and other molecules that make up the wood have a higher potential energy, and when they react with oxygen to form carbon dioxide and water, they have lower chemical potential energy. That energy is released as thermal energy, the heat given off, and some of the light given off in the flame. Anybody else have any questions or comments? So Lavoisier, who was, came up with this law, he was burning stuff in closed containers. Because if you burn the log in a closed container, then the products of the combustion can't leave. They're still in the container. The mass of the container doesn't change before and after. Yeah?
Does that mean that light is not a physical thing?
Light is not a physical thing. It's not matter. It's energy.
So then what exactly is a photon? I'm trying to understand that.
Yeah, so we will talk about what photons are later. Photons are energy, but they are extremely small, and so like electrons, they behave like a wave, like electromagnetic radiation. They also behave like particles, and this is something that is very, very confusing. But photons do not have mass. Anybody else have any questions? He's going to like chapter 7. Oh, come on. Okay, so these other two laws. Their names seem to contradict each other, but they don't. The law of definite proportions. So this is that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. And this was formulated in 1797. Oh shoot, I forgot to fix that again. By Joseph Proust, a French. Yeah, there's something missing there, obviously. Let's say scientist. I don't know what he studied, but he was a scientist. So, example here, if you take water, you can decompose water into its component elements, hydrogen and oxygen. If you start with 18 grams of water and decompose it, you'll end up with 16 grams of oxygen and 2 grams of hydrogen. And so we can look at the ratio of those masses. It's generally convenient to take the larger one relative to the smaller one so that you get whole numbers or numbers that are larger than 1. So we can look at that mass ratio, 16 grams of oxygen to 2 grams of hydrogen, a ratio of 8 or 8 to 1, right? If you took another sample of water from a different source, a different size, you decomposed it perhaps in a different way, and measured the masses of hydrogen and oxygen that you got out, the ratio would also be 8 to 1. Doesn't matter where that water comes from. Pure water always has a mass ratio of 8 to 1 for oxygen to hydrogen. That is the definite proportion. Okay? The proportion is definite, it's the same. So we can look at things like this. This appears to have a calculation in it, but it's a very, very simple calculation. So the mass ratio of nitrogen to hydrogen in ammonia is 4.7 to 1. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? Well, what that ratio says, let's just start that one over. I can't even do that. Let's erase it. I don't know what's wrong. 4.7 grams, the ratio is nitrogen to hydrogen, 4.7 grams of nitrogen to every 1 gram of hydrogen. That's the mass ratio, the proportion for ammonia. And this question is saying, well, we have a sample that has 10 grams of hydrogen. How many grams of nitrogen does it have? The proportion has to be the same. What happened to 1 to make it into a 10? Multiply by 10. So then to find the answer up here, we do the same thing, multiply by 10. And so it must be 47 grams. You've all taken a chemistry class before. And so problems like this are so simple that they're hard, okay? Because you learned about stoichiometry and you've done mass to mole rate, conversions and all of this other stuff, and so you want to pull all of that out. But in this class, I haven't taught you about that yet. And there are a couple of questions on the worksheet we're going to do on Thursday that are going to ask you to do things like this. They are just extremely simple proportion problems. And it's the idea here that's important. Okay? Bless you. Anybody have any questions? Here's a little more involved calculation or problem. So again, we approach this by reading the whole thing, pulling the numbers out, and then, finding out what are they asking us to do with this. So 2 samples of carbon monoxide are decomposed into their constituent elements. 1 sample produces 17.2 grams of oxygen and 12.9 grams of carbon. The other sample produces 10.5 grams of oxygen, 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. So I'm going to pull the numbers out and write them down. So there's 2 samples. This one had 17.2 grams of oxygen and 12.9 grams of carbon. The other sample, 10.5 grams of oxygen and 7.88 grams of carbon. I just pulled the numbers out. So it says, show that these results are consistent with the law of definite proportions. So then we need to understand what the law of definite proportion says. It says that the mass ratio of the elements in a compound are always going to be the same proportion. So if these are both the same compound, what should be true of the ratio? They should be the same. Well, it's a little hard to look at these kind of weird numbers and see if they're the same. So let's simplify them. 17.2 divided by 12.9. That gives us, the calculator says 1.33 repeating over 1, or that would be 4/3, right? The ratio 4:3. And then if we look at 10.5 divided by 7.88, calculator says 7.33. 3 sig figs with more digits would be 2/4. So that's also essentially 4/3. Are these the same compound? Does it agree with the law of definite proportions? Yes, the ratio is the same. So the law of multiple proportions, the name seems to contradict the law of definite proportions, and yet it doesn't. This slide, I'm going to go through these words, and they're not going to make a lot of sense, and hopefully it'll get more clear on the next slide. So we could state this in this way. When 2 elements, we'll just call them A and B. When two elements form two different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. And John Dalton published this in 1804. So an atom of A can combine with 1 atom of B, with 2 atoms of B, with 3 atoms of B, etc. So we could have 1A and 1B, or 1A and 2 Bs, or 1A and 3 Bs, etc. So if we looked at the mass ratios for these, the masses of B that combined with a certain amount of A are going to be related to each other as small whole numbers. So this slide has a picture. This is better. Here we have carbon dioxide and carbon monoxide. So they both have 1 carbon atom. Carbon dioxide has 2 oxygens. Carbon monoxide has 1 oxygen. Here we have the mass of oxygen combining with 1 gram of carbon, 2.67. So 2.67 grams of oxygen per 1 gram of carbon. In this compound, if we had 1 gram of carbon, we've got half as much oxygen, right? The ratio here is 1.33 grams of oxygen to 1 gram of carbon. Okay, so what the law of multiple proportion says is if you find the mass ratio for these two different compounds and then you take the ratio of the ratios, that's not confusing at all. The ratio of the ratios, you get a small whole number. Like, yeah, you're tossing all these weird numbers around and you get like 2 or 5 that comes out? Yep. So we take the mass ratio for one and divide it by the mass ratio for the other. It helps if you put the big number on top. We divide these, we get 2. What that says is that this compound has twice as many oxygen atoms as this compound. The only way that the law of multiple proportions can make any sense is if we're dealing with individual particles, because you can't have 1.5 oxygen atoms for every 1 carbon atom. It's not possible. Could you do 3 carbon atoms or 3 hydrogen atoms? No, there's no hydrogen. Start that one over. Could you do 3 oxygens to 1 carbon? Sure, that might be possible. But it's going to give you a whole number ratio. So here's a practice problem. So hydrogen and oxygen form 2 different compounds, water and hydrogen peroxide. The decomposition of a sample of water forms 0.125 grams of hydrogen for every 1 gram of oxygen. The decomposition of a sample of hydrogen peroxide forms 0.0625 grams of hydrogen for every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. So we're given the ratio for these 2 compounds. So for water, the ratio is 0.125 grams hydrogen to 1 gram of oxygen. For hydrogen peroxide, the ratio is 0.0625 grams of hydrogen for every 1 gram of oxygen. To show that this is consistent with the law of multiple proportions, we're going to take the ratio of the ratios. So we could express this as 0.125 and this as 0.0625. If we take that ratio, do it on your calculator, what does it come out to? 2. What? Yep. Small whole number. Very crude drawings. of water and hydrogen peroxide. 1 oxygen for every 2 hydrogens, or 2 hydrogens for every 1 oxygen. And here we have 2 hydrogens for every 2 oxygens. This ratio reflects the ratio from the numbers of atoms. So here, if we stay with the we've got 2 hydrogens for every 1 oxygen. So that's a 2. And here we have 2 hydrogens for 2 oxygens, and that's a ratio of 1. And the ratio of those ratios gives us that same whole number. Okay, so in 1808, Dalton explained these laws with his atomic theory. And I'm not going to ask you to just, spit this back at me, but you should understand these concepts. So there were 4 points. The first is each element is composed of tiny indestructible particles called atoms. Second point, all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. 3, atoms combine in simple whole number ratios to form compounds. And 4, atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way they are bound together with other atoms. So today we have overwhelming evidence for the existence of atoms. But in 1808, this was a big deal. Now, are all of these statements still accepted as always true? No. There were some discoveries that resulted in minor modifications to this atomic theory. Are atoms indestructible? They're indestructible in a chemical reaction, but in a nuclear reaction, you can destroy atoms. So in the Lego brick analogy, when you're just regularly playing with atoms, that's like a chemical reaction with atoms. There's atoms in Lego blocks. When you're playing with the Legos, can you change those Legos into other shapes or colors or something? No, you can't. Now, is it physically possible to change them? Well, sure, you could take a bunch of them and melt them down and pour them into a mold and make them into a different shape, right? Now, can you do that in your living room? No. So, chemical processes are stuff that happen just like regular. Nuclear processes are a special category. So, in terms of chemical reactions, this is true. Does anybody know the other one that's not quite true? Number 2. All atoms of a given element have the same mass. We're going to learn later in this chapter, we won't talk about it till Thursday though, that different atoms of the same element can have slightly different masses. Statement 4 is kind of related to the problem with statement 1. Atoms of one element cannot change into atoms of another element. In a chemical process, they can't. But in nuclear reactions, they can, and they do. Doesn't mean that we throw away the theory, though. We just modify it. Add a couple of words like, in a chemical reaction. Now it's true.